Hey guys, welcome back. We're going to talk about our precipitation theory now. I'm going to go ahead and share my screen so you can see what I'm talking about. And let's talk about what we're going to talk about for precipitation. So precipitation reactions, this is a review from chapter 4. We discussed this in 110, so we'll review that portion of it. And then we will be talking about solubility equilibria, separation of ions by fractional precipitation, and pH and solubility. So those are all going to be parts of the topics that we'll be talking about today. All right, so let's get into our topic. So precipitation reactions happen when two solutions containing soluble salts are mixed. Sometimes an insoluble salt will be produced. Okay, that salt falls out of solution like snow out of the sky. That salt is called the precipitate. So if I were to react 2Ki with PbNO3 I would end up with PbI2, which is an insoluble salt. Okay, so it falls out of solution, and that's that yellow substance that you see right there in this image. Okay, so that's what we're talking about in terms of making a precipitate. Okay, now precipitation reactions are when we have two soluble salts, so two things that are completely soluble, i.e. completely in solution, completely dissolved, and they make something that's insoluble. All right. We can talk about this equilibrium using an equilibrium constant K. Since this is for a solubility product, that's what we call this thing, we call it a KSP. So that's why this has that designation KSP, right? When we're not really interested in the formation of the aqueous component. So the reaction, as we've written it here, has two aqueous components, Ki and PbNO3, reacting to give me 2KNO3, which is aqueous, and this PbI2 salt. That's really the part that I care about, is that PbI2 salt. I want to know how that's formed, okay? And since we don't write these equilibrium constants in terms of all ions in solution, we only care about the ones that made that PbI2, then the reaction what we're actually interested in is Pb2 plus aqueous plus 2I minus aqueous going to PbI2 solid. Okay, and this is the net ionic reaction for this process. Okay, so if we talked about breaking this down into only the things that make that PbI2, that's what we would be talking about there. And we typically don't write this way, because that PbI2 is not something that appears because it's a solid. So since we want to be talking about this in terms of a K that makes sense, our KSP is usually written for the reaction in the reverse direction. Okay? So instead of forming PbI2, we talk about PbI2 solid decomposing to give us Pb2 plus aqueous plus 2I minus aqueous in this case. And so our K for that is going to be equal to the concentration of the Pb2 plus times the concentration of I minus squared. Okay, so that's how we would write our KSP. Now this is no different than what we have done in the past. Okay, so writing this K is absolutely no different than what we've talked about before. It's just we're not using every single component at this point. We're using a net ionic equation to do this. And we're talking about the formation of that solid. But because that solid doesn't appear, we want to make sure that we're doing it from solid to aqueous so that we have a K that we can work with. Okay? So this is how a solubility product is typically written. Right? Remember, we have three types of equations that we can write. We can write a molecular equation that shows everything that we're dealing with in terms of molecules. So for the reaction AgNO3, which is aqueous, plus KCl, which is aqueous, to give me AgCl solid plus KNO3 aqueous. If I were to break that down and look at the ions that are involved in doing this, the ionic equation, we'd be talking about Ag plus aqueous plus NO3 minus aqueous plus K plus, which is aqueous, plus Cl minus, which is aqueous, going to give me that AgCl solid, because it's a solid so it doesn't come apart, plus K plus, aqueous, plus NO3 minus, aqueous. Okay, so that's our ionic equation. When we talk about a net ionic equation, we don't care about the stuff that's just standing around watching. So anything that appears on both sides exactly the same way, we're going to ignore. And so we take out the NO3 minus and the K plus to just leave us with the Ag plus the Cl minus, going to give me the AgCl solid. Okay. Now, from a practical standpoint, it actually makes more sense to me to write the ionic equation first. Because in order for me to balance a molecular equation, I need to know what the charges are on all of those species. So it's easier for me to write the ionic equation first, then do the molecular and make sure that it's balanced the way it should be, and then do the net ionic from there, okay? So it doesn't matter what order you do these in. That's entirely up to you in terms of your preferences. But those are what we mean by those equations. You will sometimes get asked for a molecular and a net ionic. Sometimes it'll be all three. It depends on what they're asking for. So RTFQ, read the full question, make sure you're answering the question that has been asked. Okay, so this should be a review for you as well. If it's not, if you don't remember how to do this, talk to me. I have practice from 110 that I give to my 110 students to be able to do this. Okay, so those are our equations for that. Now, because the equations are such a big part of what we talk about in terms of doing KSPs, I want to do some practice for this. So I have asked you to write the molecular, ionic, and net ionic equations for the following. For now, we'll assume that one product, the one in bold, is a state that does not appear in the K expression, either solid or liquid. Use that product to write your net ionic equation. Okay. So, reaction of silver nitrate with hydrochloric acid to form silver chloride and hydrogen nitrate. And I want you to take a stab at this. I want you to pause here, take a stab at all of these. I'm going to walk through this with all of them in just a minute, but I want you to take a pause to try and do this on your own. Okay, so I'm actually going to take a pause here and let you do that while I try and upload a video. Sorry, I forgot to do something. All right, I'm going to pause at this point, and I will be back in just a minute. Okay, hopefully you can still see what I'm doing. And yeah, it says we're sharing, so we should be good. All right, now I asked you to look at these three reactions, right? Silver nitrate with hydrochloric acid to form silver chloride and hydrogen nitrate. Reaction of magnesium nitrate with rubidium hydroxide to form magnesium hydroxide and rubidium nitrate. And the reaction of hydrochloric acid with sodium hydroxide to form water and sodium chloride. Okay. Let's start with our first one. So silver nitrate. Now, as I said, we're going to do I'm going to write a molecular, an ionic, and a net ionic for this. I'm going to write the ionic first. So silver is an Ag+. And I know that because it's one of those transition metals that can have multiple charges. Since it doesn't say what the charge is, we have to assume that it's silver 1 because that's the lowest charge it can have. So Ag+, that is aqueous. I know that that is with nitrate, which is NO3 minus, and that's aqueous as well. So that's one of those polyatomic ions that I can look up in the table. Okay, I'm reacting that with hydrochloric acid, which is an H plus a Cl minus. Okay, and it's an Ag plus and an NO3 minus, so that's balanced as those are, and an H plus and a Cl minus, so those are balanced as they are. When that comes together, I know that I'm going to end up with an Ag Cl solid. Now we'll talk about how we know which one is solid later. Okay, we'll get back to that. But for right now, it says silver chloride is the one that's in the other phase. So silver chloride is a solid. And then I have the NO3 minus, which is aqueous, plus that H plus, which is aqueous. Okay. Now, I do have a silver, one silver on both sides. So an Ag here and an Ag here. Okay. I have one NO3 minus on both sides, NO3 here and an NO3 here. I have an H plus, one here, and I have a Cl minus, one here. I'll show you that. Come on. Of course, there. And then another one right there. Okay, so I know that this is balanced. That means that my molecular equation is going to be an AgCl, or AgNO3, sorry. I apologize. That's an AgNO3, that's aqueous, plus an HCl, also aqueous, going to give me an AgCl solid plus an HNO3, hydrogen nitrate, HNO3. Okay. And of course it's H plus and NO3 minus, so that is balanced as it is, and that HNO3 is still aqueous. Okay, so that's my molecular equation. Now my net ionic equation is the one that includes just the stuff that makes that AgCl solid. So then we're going to be talking about the Ag plus aqueous plus the Cl minus aqueous, going to give me an AgCl solid. Okay, so that's what we're talking about there. Awesome. Hopefully no questions, comments, problems with that, but if you have them, please let me know. Next, we're going to look at the reaction of magnesium nitrate with rubidium hydroxide to form magnesium hydroxide and rubidium nitrate. Okay, I'm going to do my molecular here. I'm going to do an ionic here. And then we'll do my net ionic down here. It's not a lot of space, I know. I should have left myself more room. But magnesium nitrate. So magnesium is in the alkaline earth metals. So that's an Mg2 plus AQ. And that's and with nitrate, NO3 minus AQ. If I have a 2 plus and a 1 minus, I need 2 NO3 minuses, okay, to make that work. I add to that a rubidium hydroxide. Rubidium is an alkali metal, so that's a +1. And then that's with a hydroxide, which is a -1. And that's aqueous. Oh, sorry, I forgot to split it. Rubidium is +1, that's aqueous, plus a hydroxide, which is aqueous. And that gives me the magnesium hydroxide solid, because that's what's in bold. So Mg, and it's an Mg2 plus. The OH minus is a 1, so that's my solid. And that's because it's an Mg2 plus and an OH minus. So I need 2 OHs to make that work. And then I have my Rb plus the 2 NO3 minus. Now, is that balanced as it is? Well, no, actually it's not. And so let's take a look at that. So my Mg NO3 2, right? Because it's an NO3 minus, and I said I needed 2 of those to make that work. So that's an Mg NO3 2. So that's okay. Charge-wise, that's fine. I know it's an Rb and an OH, so that's okay. That comes across and gives me an Mg OH2, which is a solid. But in order to have 2 OH over here on the product side, I need to have 2 OH over here on the reactant side, which means I need 2 RbOH. So I put a 2 out in front of that. And that's then going to give me 2 RbNO3. Okay? So I need to have a 2 out in front of the Rb here as well. And that again is to balance the charge. So that's that. Now, in my net ionic, I only care about the Mg2 plus and the OH minus, which is not balanced. So there should be a 2 here. There should be a 2 there. And then I'm completely balanced based on what I had written in the molecular. Okay. Now, for my net ionic, I'm going to need the Mg2 plus aqueous plus the 2 OH minus aqueous to give me an MgOH2 solid. Okay, so that's making sure that I'm balanced for everything I need there. If I look at the reaction of hydrochloric acid with sodium hydroxide to form water and sodium chloride, so hydrochloric acid, we've got an HCl, hydrochloric. So hydrochloric is an H plus a Cl minus. Both of those are aqueous. And sodium hydroxide is an Na plus, not a 2 plus, A plus, because he's an alkaline metal. That's aqueous. Plus an OH minus, because that's what I would need to balance that Na plus. That's going to give me an H2O liquid plus an NaCl. Na plus, Cl minus, and that again is aqueous. Okay. That molecular equation is then going to be an HCl aqueous plus an NaOH aqueous, going to give me an NaCl aqueous plus an H2O liquid. Okay. So the H2O liquid is a liquid. We leave that together. Now, does it come apart to some small extent? Yes, but it stays as a liquid there. Okay. And so my net ionic equation, the only parts that I care about that make that thing in the other phase are the H plus the OH minus, both of which are aqueous, going to give me an H2O liquid. Okay? So those are the things that I care about with that. All right? Now, obviously, when we're talking about solubility, we're more concerned about what we're making from those insoluble products, the solids. But I wanted to remind you that not everything that we care about in terms of net ionic equations is solids. That liquid formation can be something that you can be asked about in terms of molecular ionic and net ionic equations. So don't forget about that. Okay? Now, hopefully there are no questions about that. But if there are, please let me know. I will be happy to answer any questions that you have. All right? I'm just going to skip over and see. Yeah, okay. So that takes us to the end of that segment. All right? The next thing we're going to talk about is solubility equilibrium. I'm going to stop sharing and I'm going to stop recording so that we can get into that section. All right, guys. Talk to you soon.